Okay, welcome to my talk. My talk is Container Escape in 2021. My name is Li Qiang and I'm from Arms Group. So first of all, let me introduce myself. I am a platform infrastructure security engineer at Arms Group, and my work includes security research and security development, and my interest includes all of the low-level materials, for example, the Linux kernel, the virtualization, the container, and the security. I have been a security researcher for a long time, and I give some talks in Rackscore, West, and Saska. So, okay, this is the agenda. First of all, I will talk about the container escape concept. And also this will include some of the container concept itself. As we know, container is a hot topic in nowadays. And the container security is also a hot topic in security research. As we know, there are a lot of container escape methods has been talked and discussed, but as the traditional container here, I mean RunC container, share the same kernel with the host. So there are always new container escape. So in the second part, I will talk about my finding of 3 new container escape methods. This includes following. First of all, the new method is the bin format MISC. User model help escape. Then I will talk about the eBPF escape. This is not the infamous eBPF kernel vulnerability escape method, but the eBPF can be used to container escape itself. The final escape method is from the virtual machine monitor and after discuss the new container escape methods, I will talk about the defense. And here we can see how to defense of this new escape methods. Okay, let's go. Let's first talk about the container escape. Here I want to make it clear that in this talk, I mean container is the transition container. It means the RunC container, and is made up of namespace, C group, and over the FS. The container is a lightweight OS level virtualization, and the Docker is the first implementation in the industry. So I will most talk about Docker. Okay, now container is often compared with the virtualization, and they share the same virtualized runtime environment concept. Here this picture shows the virtual machine model. There is a VMM virtual machine monitor, and to abstract the whole virtual machine to the virtual machine, and the virtual machine can have different operating system, and they are not aware of they are run at virtual machine, and this is the container architecture. There is a Docker engine who is used to create container. Every container also has his isolated runtime environment. The most important difference between container and VM is that the container share the same kernel, and the VM has his own kernel. So share the kernel with the host is the biggest attack surface of the container security. Okay, so let's talk more about the container. Container is made up of namespace, C groups, and UniFS. The namespace is used to give different view of system resources to container. For example, the PID namespace gives the containers different PID number, and the mount namespace gives the container different mount point. The networking namespace gives the container different networking stacking. The C groups is used to restrict the container's resource so that the container cannot consume a lot of the system resources. For example, the CPU and the memory resource. The UniFS is used to image share and distribution, as there are a lot of containers and they can share some of the file systems. So this is UniFS what does this. Okay, and we have said, container security's root code the kernel has the biggest attack surface. This is because there is no free lunch. The container has a better performance because of share the kernel, and has less security than VM because of this share the kernel. So this makes the container and the kernel's weak isolated. So share the same kernel has been the biggest attack surface. The most severity of container security is container escape. Here, this picture shows some of the container escape methods. Mostly, it can be classified with three kind of methods. The first is container engine vulnerabilities. This means this container engine has some vulnerability, so the container can leverage this vulnerability to escape to host. And the second is the privileged cap and sensitive mounts. Every process in Linux can have different capabilities. Capabilities make Linux a listed privileged system. So if the container processes has some privileged capabilities, it can leverage this to escape to the container. The sensitive mounts means that the virtual file system that amounts to container. This sensitive mounts often are virtual file system, and the kernel exports the kernel information and control options to user space. And if this file system mounts to the container can leverage this to read the kernel information and control the kernel behaviors. And as we see, the container shares the same kernel with the host, so the container can ensure syscalls to the kernel to trigger the vulnerabilities in the kernel. So the kernel vulnerabilities is one of the source of container escape. Okay, here I will talk about mostly of the privileged camp and the sensitive amounts, and they are related with this talk. I will here I talk about three capabilities. The first is camp session module, and we can see this camp is used to local kernel module to the kernel. So if the container has this cap, it can load a kernel module to the kernel, and can execute attributability code. This is the most severity cap. And the second is the campus admin. This campus admin has a lot of privileged operation. For example, it can use to remount the read-only mount to read-write, so that we can write the virtual file systems and control the kernel. And the third is camp DS read search. This is used to bypass the read and search permissions. This can be used to read the host file in the container. The sensitive mounts is the virtual file system that kernel exports. Here shows the idea. It also exports the interface of the VFS, and in the container or normal process, it can read or write prog.fs file. Mostly, the read handler will read some of the kernel information to the process, and the write handler can control kernel behavior. Okay, let's talk about user mode helper program. The user mode helper is used to run program from Linux kernel. Here shows the normal path create a process. But the process is launched at the user space, but user mode helper is called by the kernel. For example, if the kernel decided to want to load the module, it will call the user mode helper mode probe, and this will execute in the kernel. Kernel mode helper is called by this function called user mode helper. A lot of helper has used to container escape. Here is the model. So first of all, the container writer help. For example, let's test the SH. This test has something like can do some malicious activities. For example, you can read the shadow file and put this file in this also this temp directory. Then the container process can write helper path to kernel. Here does this, and then in the host the kernel trigger the helper CVE. This can be triggered from container or the other process or the other events. And then the help will be executed and read this shadow file to the container file systems. And then the container can read this shadow. Okay, this shadow is the host's it is a shadow file. This is the container escape of user mode helper program. User mode helper, there are a lot of user mode help. For example, the model probe is used to load the module, and the call pattern is used to be called when the program has crashed. The U-event helper used to the device module, and the release agent is used in C group. The bin-format MISC is used to register a user space handler. This has been talked about, but as far as I know, there is no public exploit. In fact, the first method is this. Okay, then let's talk about the new container escape methods. The first is container escape through bin-format MISC. Okay, that's the first introduction, the bin-format MISC. It is a prog file system It is in program file system, and this bin format MISC mechanism allow kernel execute any format file to be executed. They will because the kernel can't recognize any file of this. It will call a user space program registered by the user space, and this allow attribute file format to be executed. There are a lot of use cases for this. For example, if we want to run DOS application in Linux, because Linux itself cannot execute this, but if we execute, but we register a interpreter, and then this interpreter can run our DOS application. So this mechanism makes can let the kernel execute any file. Let's show the example of bin format MISC. Here, first of all, we prepare an executable file. Here we say we create a file lambda test format, and the content is AAA. And here we can say we make it executable, and here we execute it. But let's see how the kernel will execute this. First, after we prepare this executable file, we prepare this handler. So we create a file, and we just print a test format message. And we also should make this executable. Then here we register a executable handler. This handler will match the file that begins with 3AAA. And here we can see the information, magic AAA, and then we execute the first executable, and then we can see it prints the test format message, which is the handler does. Okay, let's see the bin format internals. This is the usage case. Usage. The register interface is in this file, and we can show this with the bin format help name. We can clean it with 1 plus -1 to this. Here is the field of the data we need to register. The type means we recognize the file with magic or extension. Here with magic. And the offset means where we start to do the match work. And the magic is the data match. And the mask is used to show which byte this is valid. And the interpreter is the most important. This is the full path of the interpreter and will be called by the kernel. Here we can say the interpreter is this, and he will interpret the file with AAA at the beginning. Let's say the bin format MISC internals. Linux kernel meant format list. This list register a lot of formats that the kernel can execute. For example, the batch, the ALF format. When we do execv source code, the kernel will search the list, and if one format has been found that matches the executable file, the load button will be called, and the file will be executed. Okay, so let's say bin format MISC in this list. The MISC format entry is inserted into the head of the formats. here we can see the heads. So if two handlers match the same executable file, the MISC format is selected. This means if, for example, this format with this entry is used to process ELF. This entry is used to process batch file. But if we registered a more precious match, and if the search process finds that our bin format is matched, and it will call our handler. So this means that we can insert a new executable handler for ELF and batch. This shows the idea. First of all, we can register a handler, interpreter here in the container file systems, and it's red shadow and put here. Then the process can register a format handler, and then now the kernel has this format handler. The kernel executes, for example, if someone executes the file in the host, and then our interpreter will be called, and it will read the shadow of the host and write it to the container file system. So this is the pure shell of the container escapes through bin format MISC. Here we set this interpreter handler as this. So it just read shadow and put this file in the shadow. And here we register a handler with this. This offset means at the start, match the file at the start. This magic means that the file which is used, which begins with this strings will be matched to our handler, and the interpreter is this. So in our container, and so the host we can prepare a host bench. Here we can see this bench this bench file is matched with our pattern. It begins with this string and equal. So when the host executes this file, the kernel searches the format list, and it will find our bin format MISC is matched. So the interpreter will be executed, and it will read the shadow file and write it to the file systems. So the container can read this shadow. This shadow is the host shadow file. Okay, here is the picture of how it does. Here we start a container, and notice we need to and consensus admin. So here we remount the remount the probe size fs from read only to read write. And here we found that the file system of the container. And here we write the helper, and here we register the interpreter. So in the host we execute a matched file, and we can say it did nothing, just read etc shadow and write. So in the step 3, we can see that the temp directory has the shadow file, and we get the host file. Okay, let's see the second example of bin format MISC. Here just example for replace the ELFL handler. So we can see the LS program hex, and we found that in here we have 2 bytes. So we use this 2 as a match, and we register a handler for this file. So when the host executes ls, we can see that the container contains the shadow file. So this shows that we can replace the ELFL handler. Okay, so let's talk about the second escape methods, escape through eBPF. Also, let's first introduce the eBPF concept. eBPF is short for Extended Berkeley Packet Filtering. It is originated from classic BPF in 1992. It initially is used for packet filtering, but now it's used in a lot of places. It and restricted code to kernel and runtime. eBPF has grown in recent years very fast, just like what JavaScript does for browser. The eBPF also enriches a lot of kernel innovation. eBPF has a lot of use cases. For example, the networking, the chain, the runtime security. The first use case for eBPF is in networking. For example, you can replace the IP tables with eBPF, and also the transfer is a important use case for eBPF. And recently, the eBPF used in the runtime security. For example, the focus is used to detect the malicious activities in the container and the host. Okay, this is the architecture of eBPF. First of all, we program eBPF programs and maps, and then the LLVM compiler will convert this source file to bytecode, and we can use BPF size code to load this program maps to kernel, and the kernel will verify that our BPF has no harm to system, and sometimes it will compile it from the eBPF instruction to the machine native instruction, and so we have eBPF program, or valid eBPF program. Then it will be attached to the system call networking, capital, and LSM, and the other subsystems. Also, there is maps and helpers. Okay, some of the core concepts I need to explain here. eBPF program type is where eBPF will be executed. So when the kernel runs at the eBPF point, when the kernel point eBPF program will be executed. The eBPF map. This is used to do communication between the kernel and the user space. Also, the eBPF map can be used between the eBPF programs, different program types. eBPF verifier is used to make eBPF program has no harm to the kernel. For example, the stack usage of eBPF program is very limited. eBPF help, this is just like library, and the eBPF program can call this library to do its own work. Okay, let's talk about the kprobe and eBPF. Kprobe is a measurement that can be used to instrument the kernel and almost any kernel code address. There are 2 kprobe. keyprobe types, the keyprobe which is used to which is instrumentation and the point, and the caret probe is used to instrumentation and the function return point. The eBPF program can be attached to keyprobe. So here shows the idea. For example, if we attach eBPF to the keyprobe of kernel function and the caret probe also to this kernel function, the call path should be this: when the kernel calls this function, our first eBPF program will be executed, and then the kernel function, and then the caret probe eBPF program. The eBPF program can print data to the transfer pipe or the perf buffer. Okay, let's talk about container and eBPF. Container, both eBPF and the keyprobe is not aware of the C group and the lamp-strip, so they are system-wide. So if the container has camp size admin or camp BPF, it can load the eBPF program in kernel. Notice this is system-wide. So the container can read or control system level behavior. So here shows the container escape through eBPF. So the container first attach a eBPF program in the VFS read caret probe, and then the host read when the host read etc shadow or any file, the VFS read will be called, and it will read etc shadow, and between its return, it will call our eBPF program. In this place, the eBPF can read the data what the VFS read have loaded, and so the container will get this data. So here shows the concrete POC. So first of all, the container attach caret probe to this, and then it read the transfer pipe, and when VFS read etc shadow, it will load the data into memory. And some register will point this, for example, R13, and so the eBPF program can read from this register and print this buffer to the container. Here shows the concept. Here shows the POC picture. Also, first of all, we start a container with sysadmin, and then we mount transfs. Here we create a caret probe of VFS read, and we load this program. We load this eBPF program in kernel. So in the second terminal, we read this transfer pipe file, and in host we can read etc shadow file, and we can see here we read the file of the etc shadow. So this demonstrates the container escape through eBPF. In fact, there are several topics about eBPF can be used as a rootkit. For example, they can read the host file. They can hijack the execution. So here is this just a POC to demonstrate that we can escape through eBPF. Okay, let's go to the final methods of container escape. Escape from virtual machine monitor. Nowadays, the container is often run in a VM, and so they can benefit from both architecture. For example, the VM can be used in very a flexible way, and the container is also. So here we often see architecture with this, the QMU virtual machine and run the container. But we need to know that the VM attack surface has vulnerabilities. The interface between VMs and QMU devices is a lot of vulnerabilities. So the VM can read a lot of data to the devices, and if this VM has vulnerabilities, the VM can trigger this. This is a typical virtual machine monitor vulnerabilities. The Linux kernel exports device and driver when the driver information through SysFS. This SysFS is like also a virtual file system like progfs. It's usually mounted at the site, and it contains device and driver information and can control device behavior. For example, this is a typical information about the device information. Here we can see that it has a PIC configuration. It is write and read. Also, the resource 012 is MMIO resources. It is also read write. So here we can see the devices, the driver in the VM can trigger vulnerabilities in QMU through MMIO. So if we export this SysFS to the container, it can also trigger the vulnerabilities through user space by writing this MMIO. So here shows the idea. And the container can interact with the device through the SysFS. Of course, if we need to capture the domain to mount SysFS and remount the SysFS from read only to read write. And if the virtual device is variable, so we can read and write the MMIO of the device in container through SysFS interface. So here the POC I used is changed from the scavenger from Pangolin and Li Qiang. Just the POC change from here. I just changed this. So here shows. First of all, I start a QMU virtual machine this, and then I run a container, and I give this campsite admin on the compatibilities, and then I install some of the package, the build package. Then in the QMU VM, I mount the SysFS from the read only to the write. Then we execute the exploit. Then in the host QMU process, I give a call. The QMU process crashed. So this here is what here I see what it does. So in the container, we trigger the vulnerabilities then QMU through the SysFS. We write the MMIO and trigger the vulnerabilities in QMU. So the QMU crashes. And this topic is not about VM escape, so I will not show this in a total. So just the POC that can demonstrate the idea. So let's talk about how we can defend of this. And we can say the bin format MISC is a common user model helper escape. So there are several methods to defense of this attack. The first thing is using secure container. For example, the G-Visor Kata, because secure container has a separate kernel for the container. So if they will not share the kernel with the host, they can't harm can't change the host's user mode help. Then we can drop camp session admin. So this way, we can't remount the prog fs. We can also use the user mode help whitelist. For example, the kernel contains a configuration for this. Also, if we have used the LSM in production, we can also open them. Okay, for the eBPF escape, also first of all, we can drop the camp session admin, can't remount. Then we can disable unprivileged container of the eBPF. This is not an upstream solution. Then we can also just allow the signed eBPF program to be loaded into kernel. This is in progress. In fact, the eBPF program escape has been demonstrated as a very powerful. So we need to harden this. For the VMM escape, also we can security container through secure container, and as the vulnerabilities in the container itself don't infect the whole system. Also, we can drop the camp session admin. So this we cannot remount the file system. Also, we need to track and fix the virtual machine monitor vulnerabilities. Okay, this is all my talk. In this talk, I have talked about 3 new methods on a bit container escape. The user mode help is exploit, and the container escape through eBPF is used to container escape through eBPF program. And finally, we need to also focus the security of virtual machine monitor who as the infrastructure as run container. Thank you.